All right. So I realize you already heard a lot about the Lee-Yang, so I'll try to be very concise with our results. This is, as I said, working collaboration with Olivier. All right. So before I explain this plot, and we've seen cartoon versions of it, but you haven't seen yet the 3D version of this, which is this plot over here. So here, criticality is, or pseudo-criticality is obtained simply by the collision, okay, of the states. And okay, in the x-axis is h. I'm using the same Hamiltonian as U1, so I'm only tuning one of the pseudo-potentials. So there are this number of parameters, the ones of the Ising plus the new parameter h. And as we are at the large h, and we increase g, we hit this critical curve that has been appearing a number of times, right? So let me very briefly tell you what is the idea that we came about for tuning the model, which is slightly different than the previous talks. So at the beginning, we were faced about the question about how to, because as you increase n, we observe that the critical curve goes down. And the first question we were asking ourselves is, at finite n, what should be the best value of g where the Lee-Yang lives? Should I stay arbitrarily close to the critical line? Probably not, because it's going down. So how much into the bulk we should move on? And also how to tune the alpha parameter of the Hamiltonian. That's the two questions we're confronted with. So we came out with an idea that eventually is similar to the tuning that, let me tell you the idea. So the idea is that we're going to consider this chi-square function, and there are many moving parts here. So first let's take a slice on h. So I move inside, and I'm going to evaluate this chi-square as a function of g in this slice here, the red vertical line. And for the starters, because the epsilon-expansion is so precise, as it was reviewed very nicely by Joan, I'm going to input the value of delta phi. Later on, we are going to try to estimate. But first, I want to tune the model with the given value of the epsilon. So this is the chi-square, and I'm going to evaluate it along this line. And then we're going to evaluate a second chi-square where besides the expectation from conformal perturbation theory, we also add the leading relevant perturbation with a G phi coupling. And we are going to compare both of the values of this chi-square along this line. So this is what you get. How you should read this plot? Let me just emphasize very quickly what are the important features. So critical coupling is roughly here, okay? And as we move to the left of this plot, we are going down here. We're going to lower g's, right? So first, we observe that indeed this chi-square has a nice minima inside for lower values of g. Okay, which is what these curves are showing. And then the chi-square that involves this first order conformal perturbation theory from the relevant parameter precisely crosses 0. So g phi as a function of g. So g phi is retrieved by this minimization, crosses 0 at the same point where the minima of the other chi-square is obtained. And here is also the alpha, which is the alpha value, the normalization of the Hamiltonian, which is relatively flat. This qualitative behavior was also found in the cosaedron feeds that Slava and Lau did, as far as I remember, where when you first do this minimalistic chi-square, you find a nice minima. When you add the leading relevant, you see a very pretty flat chi-square, but with a nice feature that the relevant parameter crosses 0. So this qualitatively is pretty similar. So right, with this we extract g phi and alpha for a given h. Now the next question or the next moving part is let's do the same but for different slices as a function of h, and let's see what happens. And here we obtain independently a similar conclusion to the one that Joan said, which is that there are some benefits in going to larger values of h, so be very, very far from the critical Ising, and then turning on the imaginary coupling. So we see that there are some benefits, but these benefits are limited, namely that we went to pretty large h's, and eventually we see that the minima of the chi-squares go up. So there is some optimality here at a given volume to how much large values of h you want to take. All right. So with this, we learn how to tune the Lee-Yang model with these simple observations. So now I'm going to show you how the spectrum looks at this start point. Okay. Let me emphasize the first two conclusions that I got, which is that we tune the model by minimizing this minimalistic chi-square, and that we find a G minima that is below the naive pseudo-criticality, and the large values of B0 and H are favored. All right, so this is how the spectrum looks right away there. So here you should be looking at the blue points as a starter. So the spectrum looks relatively well aligned. Here again, I insist that this plot has some implicit dependence on the delta phi, which was used as input to these minimizations. Okay. And later on I will show you more multiplets. In this plot I'm showing you the phi multiplet with fewer descendants up to spin 3 and the T mu nu. And without this doesn't contain any large extrapolation. Okay, this is n equals 16 data. All right. Now the deviations are pretty small from what you would expect from the conformal spectrum. So this calls for an effective field theory fit, just to try to understand what are we missing here. And well, a nice observation here that is going to be useful later on is that so now we add the leading operators, which have already appeared in the previous talk, which is going to be the phi cube operator, okay, and the spin 4 operator. And the spin 4 here is important to add, because if we only add these operators, so these operators are going to ship with certain patterns, up and down the various corrections. But the precise pattern that we get doesn't match the data. So really this leading Lorentz breaking is called in order to explain the data. So then when we add this BC operator, this the BQ in the previous talk, then we get a precise agreement for these deviations. I'm not sure it's here written. No, but it's below 1%. So now you should be looking at the crosses, not at the blue point. Now you should be looking at the crosses, okay? So the crosses have tiny errors, okay? All right, so given this preliminary success of how the data looks, then we made an attempt to now estimate delta phi independently from the phi sphere. So what is the next logical step? The logical step is to repeat all what I said by changing the delta phi input parameter. Namely, we're going to again find the best value for G on this chi-square by using a number of different delta phi's. Okay. Sorry, I'm getting ahead of myself. Let me take a step back. The next logical step that we're going to do for extrapolations, apologies for the confusion, is let's repeat all what I said, but first as a function of n, okay? And as a function of m first. So as Joan said, the nice thing of the phi sphere is that there are many observables that one can measure from the Hamiltonian, which have the same prediction from at large n for the CFT. So in this case, we built these many ratios, okay? All of which should give delta phi, right? So this what is being showed in this plot. The points are values at fixed n, okay? And then we do an extrapolation in this case, which is slightly different from the previous one in the sense that we only include the two leading irrelevant operators, okay? Phi cube and C, that as we saw previously, was important to add. And then, because, so on the left you see the extrapolations nicely match what we would expect from either the input delta phi that we add, so this self-consistent, the whole procedure, or with the epsilon. Now the other nice thing here is that alpha is was not determined by fixing T mu nu. So here we can also have a chance to make a prediction, which is what is the large chain extrapolation for the spin 2 operator, and it nicely extrapolates to 3. Okay. So now, so this shows that the large chain extrapolation nicely works, and it's self-consistent, the whole procedure. So now is the next step, which is let's try to do an estimate for delta phi. Okay. And here our results deviate a bit in the following sense. So now the idea is repeat all what I said, but now varying delta phi, namely, let's determine a critical g at a given n by minimizing the chi-square, and this has some input from the delta phi. Right? Then what we saw is that this procedure that I explained here, at least for the amount of data that we use, didn't have a very we see that varying delta phi within 20%, we get a nice extrapolated spectrum. So that's so far the conclusion we got, that the phi sphere spectrum is compatible with all these, and it aligns nicely with the CFT expectation. On the other hand, we saw that from the previous talk, Joan, that he had a very precise values of delta phi. So what I can say is that we have larger errors from this measurement. Or this we cannot claim smaller errors. So here are some ideas on how to improve our analysis. Well, our analysis was based on effective field theory, and I can tell you something which is unpublished, but so if you take, so what we expect is that if you add many more conformal families, this should help a lot in discriminating power, okay? If you take the Ising icosahedron that has appeared a number of times, you can ask yourself whether you can, so you should fit this Hamiltonian with some effective field theory that has the same symmetries, and of course the primary one that you may think is precisely the Ising CFT, but okay, you could try to fit with another theory, like the free theory, okay, and like you could try, because you could try to test whether the data is just compatible with both IR effective field theory or is clearly skewed to one or the other. So the point is that for either for the icosahedron or the dodecahedron, when you do this exercise, you are only like pulled to conclude that you are in the Ising if you start including several conformal families, if you start putting epsilon prime and so on. So that's where I believe that our analysis could be largely improved if we put those. And finally, obviously, increase n. Another thing that that we didn't put on the paper and none of us has done, none of the groups, is to put the matrix elements from conformal perturbation theory in the IR fit. This is a prediction that has not been included by any of us. We tried, although we didn't put in the paper, we tried because for the moderate ends that we have, we then saw a large improvement by including those. But there are things that when you increase n should leverage a lot on the fit, because it's going to be much more constraining that you fit all the lines with a particular pattern. Okay, so that's some first statements. But anyways, the last step, let's take all our data and extrapolate it with a well-inspired effective field theory function, which is this one over here. This contains roughly the phi cube interaction and the spin 4, and we get a spectrum of multiplets. Here I'm showing you up to spin 4 and dimension 5.5 roughly, where we recognize that the multiplet of the phi family nicely align. We also observe the phi cube operator and the spin 4, and okay, the agreement. We have general agreement with the previous speakers. So that was a concise summary of the way we fit it. I think that was useful. Let me make a very rough summary of what you have been exposed to today. So I think it's fair to say that the first group had an impressive tuning using pseudopotentials, although at the caveat of being at lower ends. So there was more emphasis on this, on more pseudopotentials. Previous talk and myself, we did the same Hamiltonian, same number of parameters, but we went to larger ends. Joan had besides these nice extrapolations and new estimates from the epsilon-expansion, which are very nice, he also has this 2D revision of 2D with that was not previous in the literature, and it's nice. Plus all these cool polytopes, which generalize this work by Lau and Richkov. And instead, in our results, we're somehow we put much more emphasis on the EFT, on the IR-EFT prediction. Last comment here was already mentioned by Joan, that perhaps one can create, this virtuous loop between Gliozzi bootstrap approach now and the Lee-Yang, and as he mentioned, there are many other phi cube type theories that would be nice exploring. So let me finish with I want to finish with a wild speculation, okay, and tell you one of the secret reasons why me coming from high energy I had some interest on the non-unitary models, okay. So these are the wild speculation. So as I said earlier today, there is this nice Cardi-Musardo matrix that already hints at this funny thing, that Lee-Yang plus phi is a pseudo-Hermitian theory, yet has a unitary S matrix. Okay. So now I want to consider a slight generalization of this idea of Musardo and Cardi. So it's known for a while, thanks to this paper by Dore and Tateo and Dunning. In that paper, they studied many two-dimensional RG flows, okay, between non-unitaries. But there was a particular one in that paper that showed that the M38 flows to the Ising in 2 dimensions. And now recently, there was this nice paper by Klebanov and company, which gave a nice semi-classical interpretation of this M38 model, which are these 2 phi cube interactions. So we have a Z2 even field, sigma, and the phi, which is Z2 odd. Okay? And it's very analogous to the Lee-Yang. So you can think of sigma as the Lee-Yang field, and phi sort of a Ising field. Okay? And this has later on, Tanaka and Nakayama have been using non-invertible lines, have been able to put even in more solid ground the 2D part of the story. But this idea of Klebanov, it's valid throughout d equals 6 all the way to 2. Okay? Now here, so something I'm interested is about the S matrices that arise in these RG flows. So why so? There is a curious observation, which is that in this RG flow between the M38 and the Ising, this idea has appeared before in this workshop, and some people in the audience know very well that the Wilson coefficients of the effective field theory in the IR are constrained to be positive, okay? The leading coefficient. So in particular, if you flow to the Ising with Tt bar, this coefficient should be positive. And this assumes a number of things, this theorem about the positivity of Tt bar. But the nice thing of that this provides like a well-defined example, so you can compute it. You can compute it using because the exact vacuum energy of this system along this RG flow is known, and you can compute it and extract the Wilson coefficient of the TT bar, and it has the wrong sign. Okay. From the semi-classical description, this is rather obvious, because when you are close to perturbative theory, to the 5D, you are just integrating a ghost, okay, which is the sigma field, which is a ghost particle. But when you go to strong coupling, this ghost, so when you go to strong coupling, the theory becomes like more consistent, in the sense that this ghost goes to the imaginary axis, and you are left with a unitary S matrix. So this is, I don't know, I found it very curious. And so why is it possible that the C is negative, yet the S matrix is unitary? Of course, you're evaluating some assumption, and the assumption is that there is some pole deep in the complex plane. But unitary is perfectly fine on physical energies. We are always unitary in physical energies. And the issue why you get positivity violation is not because the UV fixed point is non-unitary, but it's because of the pseudo-emission of the Hamiltonian across the flow. And this becomes more evident with the following, which is that, in fact, you can go to the M3A by some perturbation. So you take two Isings, and there's a perturbation that goes from the two Isings to the M3A. So, in principle, you could imagine that you get with a negative sign from a theory that in the deep UV is actually unitary, which is these two Isings. So what goes really wrong, of course, is that you are turning complex couplings in between. Okay? But yet again, the nice thing is that the S matrix is unitary, even though it has this. Okay, this may be a nice laboratory. At the very least, it's a nice laboratory to understand, in a well-defined framework, to understand what it takes to violate positivity of the Wilson coefficient. This is at the very least a cute thing. And the wild speculation, which I put in a lower opacity on the slide, okay, is are these perfectly valid S matrices? And can we understand more generally what is the mechanism by which this non-unitary theory, which has non-unitary observables, but somehow it splits out a unitary S matrix? Can we understand this better? And well, there are like very weird theories which go under the name of Lee-Wick. So Lee again work on this topic. They are slightly infamous because they seem to have ghosts and they don't seem to be fully consistent. But perhaps we can bring them to a new perspective with this point of view. I should say before I finish that this negative sign has a wrong thermodynamics, but the free energy is well defined. Only that, so what is wrong is that there are derived thermodynamical quantities, like the speed of line, which is well known, it was pointed out by Katz and Fitzpatrick, that the speed of sound is negative with negative TT bar. We should acknowledge that. But anyways, okay, thank you.
Thanks, John, for bringing this particle physics streak into this conference. Any questions or comments?
So you mentioned that to do this conformal equation, right, you need to include right conformal families, right, to distinguish, for example, Ising from Gaussian.
Yes. Yes. Yes.
So then, are there any guidance, like which family we should choose and so on?
Well, in the case of the icosaedron, you just add the next leading family, and that's already enough. So when you start adding epsilon prime and
Epsilon, because we studied sigma and epsilon family.
Epsilon prime. You add epsilon prime, right?
No, but there are two issues. There's a family which you study.
Yes, sigma and epsilon. Yeah.
Sigma and epsilon.
Yeah. No, so the guy and yeah.
Yeah. When you say this becomes unitary, you say the Hilbert space is positive definite, but is it unitary evolution as well as a scattering process?
Well, here is where the conversation can. No, I understand.
Negative norm states, but is it also unitary evolution?
So that Hamiltonian doesn't lead to unitary evolution right away. So there are a number of claims in the literature that you should change the metric in the Hilbert space to take into account the PT symmetry.
Okay. but you meant positivity, yeah.
Okay.
Yes.
Yeah, good.
So it's a very naive question related to that. So usually you can see non-Hermitian Hamiltonians as not very good physical limits of Limbaladian process, which are positive, definite, well-defined, and everything like that. So could you imagine a modification of your Hamiltonian trying to introduce properly some sort of dissipation channel to regularize the positivity of your theory, and still having these non-unitary flows?
Okay.
Well, maybe we can.
Maybe you can explain this better.
I have a question which may or may not be related, which is you mentioned the connection, how this was historically came about by Lee and Yang studying the zeros.
Yeah.
But is there a physical system where you just directly see, like in Ising, where you create a physical system and you see a phase transition and you measure the critical exponents? Is there something like that for Lee-Yang, or is it only this more abstract sense where it's about the condensation of the zeros of the partition function?
So you're saying to study the criticality of the Ising by studying. I'm not sure.
Is there a physical system which is described by Lee-Yang?
Yeah, there is.
There is, which is?
What is it?
Oh, well, sorry. There is these statistical models, like these animals and these, no? Well, I know I haven't studied the papers, but there are statistical models with this problem of counting. There are these things of animals where you need to count all the configurations of how you arrange these cubes, right?
And then this number has some function which is, you know better the story perhaps.
Yeah, so there are some so-called brushed polymers. So these are some analogs of polymers of some wooden box and so on. And there is a theorem that if you study statistics of brushed polymers in 5 dimensions, then it's, which you can very well do by Monte Carlo, then it's the same, it has exactly the same critical exponents as Lee-Yang in 3 dimensions. And there is this mismatch by 2 for any D.
But not an experiment you can
Yeah.
make in the lab, unless you can make 5 dimensions.
Well, in a lab you can, of course, do brushed polymers in 3D, but then you will see critical exponents of Lee-Yang in 1D.
I see.
These things are.
Uh-huh.
There's another answer to your question, though, which is an unpublished observation of Durham Grover, which is that consider a system which has a first-order transition. So think about the free energy has 2 minima, one of which is bigger than the other, and then vary the parameters so that here's the experiment. Prepare the system in the metastable state, and then vary the parameters so that minimum disappears.
This is called the spinodal. And
There will be critical behavior described by. Yeah.
right. Okay, well, let's thank John and go get
Just
something.
had one
There's no
comment
question?
on the structure
Of course, yeah.
factor. I mean, it has been calculated at least to 1 loop order for 555 in the epsilon expansion also, I think, maybe 2 loop order.
Okay. So you can give it a reference.
Yeah.
Yeah, Kai worked a lot on the Okay, so time for a drink. Thanks, John.
Thanks.